All right, so we all know it's a very exciting time right now in the field of AI, with innovations happening around large language models, what feels like almost every day. And what's even more exciting is that these same innovations are driving progress in robotics and taking us closer towards a future with general purpose humanoid robots that used to be purely science fiction, but now starting to look like a real possibility. So Google DeepMind had three big developments earlier this January, which they outlined in their blog post, Shaping the Future of Advanced Robotics. And in this video, I'll be breaking down one of their papers called AutoRT, Embodied Foundation Models for Large-Scale Orchestration of Robotic Agents. So firstly, taking a look at the abstract here just to get a general idea of the paper. It talks about how recently foundation models have been trained using internet scale data to gain a great understanding of the world, but we lack this data for the physical world, which is why we've had trouble training foundation models for robotics. So they've developed this new system called AutoRT that uses existing foundation models to scale up the deployment of real-world robots for the purpose of data collection with minimal human supervision. So the whole point of this paper is that they've created a system that leverages foundation models to collect lots of real-world robotics data, and this data will be necessary for creating robots that understand the world well enough to do things like household tasks and household chores. So the specific foundation models they've used are VLMs, or visual language models, and LLMs, or large language models. And you're probably already familiar with LLMs, but if you're not familiar with VLMs, they're the same concept. They're just multimodal, meaning they're able to ingest both text and images and understand the relationship between them. So AutoRT uses VLMs for understanding what the robots are seeing as they navigate through the world, and then LLMs are used for generating tasks that robots can complete based on what it sees, and we'll get more into the details of that a bit later. So moving on to the introduction, they talk about how one of the main goals of robotics research is to create these independent general robotics agents that can be given high-level goals like keep the kitchen clean and formulate plans for tackling those goals, and then have the ability to actually carry out those plans in the real world. But performing a large variety of tasks in diverse settings requires a generalist agent that can adapt to new scenarios outside of where it was trained. And in order to create this agent, lots of real world experience outside of the lab is necessary. So the focus of this paper is on how agents can be designed to gather robotic experience for themselves at scale. And they named this new system for large scale orchestration of all these data collecting robots, AutoRT, or Auto Robotics Transformer. The way these robots will collect the data is basically in a three-step process. So the first step we talked about before is the scene description step, or just describing what the robot perceives in the environment and what objects are there. And the second step is called like a task proposal step. So it suggests possible things that the robot could do with the objects that it sees. And finally, there's a step called the affordance filtering step, which decides which tasks to attempt based on the observations from the robot and a prompt that's specified by the user. So what's another thing that's really interesting about this paper is that they use this concept called constitutional prompting, where the user can define rules about the robot behavior. And we'll see more on that later. And just to understand the scale of data collection that's possible with this system, so they did extensive real-world evaluations over 7 months and 4 different office buildings and a fleet of over 20 robots, which resulted in collection of over 77,000 trials. And of course, these robots still have some degree of human supervision. So they stated that one human was supervising 3 to 5 robots at a time. So what's really novel about AutoRT to me are 3 things. So firstly, the sheer amount of data that can be collected with this system. Secondly, the diversity of the data that can be collected with this system. And thirdly, how it aligns the robot behavior to human preferences using the robot constitution. So we can take a look at what AutoRT actually looks like in the real world. So they released this little demo video, and you can see all these robots in one of their um, environments. It seems like a little kitchen environment, some tables over there, and you can see how they're all going out into the real world and trying all these tasks. So it's pretty cool. So next, looking at the related work. So there have been some attempts at real world data collection before, but most of them were conducted in a constrained lab environment, not really out in the real world. So the data being collected with AutoRT is a lot more diverse. It's not just lab data, it's like real world data. And additionally, a lot of previous efforts either had robots collecting the data entirely through automated methods or entirely through teleoperation. But there's strengths and weaknesses to both of those approaches. And what's novel about AutoRT is that it makes use of both of those methods. And this work builds on a lot of recent work focused on leveraging LLMs to generate behavior for robots to perform in the real world. So next, looking at the problem statement. So the goal is to build a system that enables large-scale data collection to generate diverse real-world data on new skills and new environments. And we assume access to a fleet of end robots capable of navigating across buildings and manipulating objects. And the goal is to have a single system that can handle any state S in S, or the set of all possible states, and generate tasks T that are executable by one of K different collect policies. So what is meant by a collect policy? Basically, a collect policy is just a means by which the robot is going to carry out the task in the real world. So the first type of collect policy is just an autonomous policy, which the robot tries to carry out on its own. So I think the one they used was RT2, or Robotics Transformer 2. If you're not familiar with that, it's one of their previous works. Basically just a model that learns how to do manipulation in the real world. It's called RT2. So the second policy that can be used is a teleoperation policy. So a human will take over and teleoperate the robot and actually complete the task. And the third one that can be used is a scripted policy, which means the robot still completes the task on its own, but using some predefined scripted algorithm for manipulation instead of some learned policy that it got from interacting with the environment. So the first thing that the robots have to do when they're set into the real world is to explore and navigate to some target. So the first thing they do when they explore is they map out the scene. They map out the room that they're in, and the way that they do this is through a natural language map that uses a visual language model to encode the object detections that are being perceived through the camera into visual language embeddings. And these embeddings correspond to a specific position that's determined by the robot's depth sensor and use of some other localization algorithms like SLAM. So once they have these embeddings, they use these embeddings to then sample for new objects that have further away embeddings to get more diverse data. So the intuition behind it is they're always looking for new things to interact with. And for each environment, a map of regions of interest is generated only once and then copied to all the robots that are collecting in that space, and then loaded from a cache to save time in future episodes. So I found the next part very interesting, and it's this concept that they use called a robot constitution. So the whole point of this constitution is to make sure that as these robots are navigating through the world, they're doing so safely. And we do this by giving the robots a set of rules. So this set of rules can be split into three basic categories. Firstly, foundational rules that govern the robots in general and define how they're supposed to interact with humans. And secondly, safety rules that describe what tasks are considered unsafe or undesired. And they also discourage interaction with humans, animals, fragile objects, and electrical equipment. Um, and then thirdly, embodiment rules that describe the robot's physical limitations, like its maximum payload. For example, it shouldn't try to complete a task like picking up a table because it's simply not strong enough to do that. Right? And another limitation is the fact that the robots are unimanual, for example. So they shouldn't try to complete tasks that would require two hands because they only have one, right? So those are the type of things that get specified inside the embodiment rules. And we can see an example of the prompt that's used to generate these rules, or the prompt that they use in the actual research paper. So if you look at the foundational rules, so they tell the robot, first and foremost, a robot may not injure a human being. Secondly, a robot must protect its own existence as long as such protection does not conflict with the first rule. They give some safety rules, like don't do any tasks that involve humans, animals, living things, don't do things with sharp objects, and the same embodiment rules that we talked about before. Okay. So this diagram helps to understand the cycle that each robot will go through. So first and foremost, the robot explores and it either maps the environment or loads the environment from a cache like we talked about earlier. And then it moves on to task generation. So the first thing that it does is it uses its visual language model to take what its camera is currently seeing and get a description of what it's currently seeing. So the example description here is, I see a countertop with a sponge and a cloth on it. And from that description, we also get a list of objects that are currently in front of the robot. So the objects are soap, napkin, snack, cloth, and sponge. And then we can feed that description of the scene as well as the objects that were in the scene into a large language model to generate tasks. And the large language model also takes some sample prompts. So part of the prompt is the constitution that we just looked at before, and some of the policies that are available to the robot for completing the task. So we'll get more into that later. But basically, the LLM takes in what the robot sees from the environment and uses that to generate tasks. So in this case, some possible tasks that the robot can complete are wiping down the countertop with the sponge, or placing the soap onto the countertop, placing the napkin onto the countertop, so on and so forth. And then it moves on to the affordance step, which basically is looking at the tasks and figuring out in what way could the robot actually complete those tasks, or what policies could be used to complete those tasks. So we see for task one, wiping down the countertop with a sponge, the LLM recognizes this is probably not something that the robot can complete on its own, or knows how to complete on its own. It would require teleoperation. Same thing for the second task, but the third task, that's like place the napkin onto the countertop. Okay, the robot can use a previously learned model, it's RT2, to actually complete that. So that's why it labels this RT2. This is the policy that it can use for this task. And then, for example, there are some tasks that are sometimes generated by the LLM, which aren't completable by the robot at all, like folding the cloth into a neat square. So you can see here that the robot rejects this task because it would need two arms to do this, and it can't do that, right? So then it samples one of the tasks that it actually can do. So it chooses one of the tasks that it actually can do, and then tries to do it and collects that data. And then after that, it comes up with a diversity score for that task, and we'll get more into that later. And then it resets and restarts the whole process over again. So as we discussed before, the task generations can be broken down into two steps. The first of which is the scene description, where the given camera image, VLM outputs a description of the scene and 5 objects from the scene. And then the second step is the task proposal, where the LLM is prompted to generate a list of tasks given the objects in the scene. So the prompt begins with a system prompt. I thought this part was pretty interesting too. So for example, a prompt example system prompt might be, I am a robot operating in an office environment. Um, and then it continues with a list of rules to be followed that are codified by the robot constitution that we saw earlier. And then the scene and the object descriptions are injected. And I think they give example of this. Yeah. So this is an example prompt given for when the robot is using the RT2 policy. You can see there it says like, "Hi, I'm an ethical and law-abiding robot that respects the following rules," and they specify the rules, blah blah blah, and then they also specify the tasks and the scene that it's looking at. So you can look more into this, but it's pretty interesting the example prompts that they give the robots. So the next step after the task generation is called the affordance step, which is really about classifying the generated tasks into a category of being executable autonomously, executable via teleoperation, or not executable at all. An interesting detail is that before being classified, there's an extra step of task filtering that's done using another prompted LLM, kind of like a self-reflection, where one LLM is prompted to critique its own output. After that self-filtering happens, then the list of collect policies are given with a summary of what each policy can do. And then for each task, the LLM must output one of the collect policies or a region to reject the task. And that's just what we saw in this diagram here. So for each task is outputting one of the policies, which is either teleoperation, completing the task using RT2, or it could be the scripted policy, or a reason for rejecting the task. Like in this case, the reason is that it would need 2 arms to complete it. So any number of collect policies could be used, but as we discussed before, they use 3. They use teleoperation, a scripted policy, and RT2. And they want the data to be as diverse as possible. So after manipulation, the episode's diversity is scored, and we'll go into more details about that. And after the scoring, the robot restarts. And another interesting detail is that they encourage task diversity also through the prompt. So a line that they add to the prompt in the task generation says none of the tasks that are generated should be simple pick and place. So by adding that there, it encourages the robot to come up with more creative tasks to be completed with the objects that are in front of it. So of course, with deploying robots into the real world, there has to be some safety guardrails there. And they added these during data collection. So they add some safety guardrails with the robot constitution and things like that on the prompts. But even with the prompts in the constitution, LLMs have no guarantees of still generating safe tasks. So the following guardrails are put into place. I think they specify those here. All robots will pause motion if detected force on joint exceeds a certain threshold. They can immediately be disengaged using a physical stop button. Unless the workspace is barricaded, at least one human must supervise the robot within the line of sight. And unsafe objects are proactively removed from the environment. And human experts sanity check tasks when they're delegated to humans. Things like that. Just safety guardrails to make sure that the robots don't do super dangerous tasks that could hurt either themselves or others. So we saw before that any task that is completed is scored for its diversity. So specifically, diversity is considered across 2 different axes. So firstly, visual diversity, or how diverse are the collected trajectories visually. And secondly, language diversity, or how diverse are the natural language instructions proposed by the system for the task. So the language diversity is measured using the L2 distance in the language embeddings. And the visual diversity is measured by doing a visual encoding of the episodes using some visual encoder, for example, a clip, and then a clustering method like k-means. They also judge the generated task based on feasibility, or is the task possible, and relevance, or does the task follow the high level guidance of what it's actually supposed to be doing. So I think they show a table for this. Maybe that table comes later. Anyways, yes. So looking at affordance and robot constitution, from the affordance step, generated tasks are also evaluated based on a couple of metrics. So the first one being the percentage of tasks that are safe, and the second one being a measure of recall, or how often the self-critiquing step that correctly that evaluates the tasks that are first generated correctly rejects unsuitable tasks during that proposal step. They also evaluate the robot constitution, and it's pretty interesting how they evaluate that. They do so by adding unsafe tasks and unsafe prompts to the constitution, and it basically shown to have a super large effect on the number of safe tasks that are generated, showing that the prompting and the constitution actually does make a difference in terms of the robot aligning itself with human behavior. To check if the data generated from AutoRT could actually bring improvements to a model, they co-trained RT1, or Robotic Transformer 1, on this data, and they found modest improvements. They say that the reasons the improvements weren't very large is that the data is very diverse, which results in a problem that's pretty hard to fit, even with state-of-the-art models. However, the point of AutoRT is to be able to generate diverse data, not necessarily to train a great model on it. But once state-of-the-art models catch up and can effectively fit this data, I think the capabilities of the models that can fit this data will be very impressive. So in conclusion, AutoRT is a big step towards robotic foundation models, but the current approach still has a number of limitations. Namely, it relies largely on scripted policies, so more diverse autonomous collect policies are still needed. Secondly, is that errors in the scene description from the visual language model and errors in the large language model hallucinating objects can be a bottleneck. Thirdly, the data collected tends to be very diverse, leading to fewer samples per task, which is a hard to fit problem. And finally, prompting an LLM doesn't guarantee the prompt will be followed, so some unsafe tasks will still be tried. So future work is that the robot constitution still needs to be improved. And also, while AutoRT is mainly focused on generating more data and not improving the model, future work could focus on combining these two tasks. So all in all, I think it's a very exciting development and a big step forward in the world of robotics, but I'm interested to hear what you guys think as well. So thanks for watching. If you enjoyed this, please hit the like button. And if you haven't already, make sure to subscribe, so I'll be covering more AI papers, particularly robotics AI papers as they come out. Thanks.